Jacobian of the generic fiber, namely, so then Qx over S is a neural model x0 x over S, sorry, xk over k. So where Q x over S is a quotient of the subscheme of the, well, say, subsheaf of the Picard sheaf, namely the quotient of the, so the subsheaf classifying line bundles of total degree 0, quotiented out by the closure of the unit section. So this was defined in a somewhat ad hoc way, because this big square bracket 0 is not necessarily a scheme or even an algebraic space. So we'll finish the proof of this, and we started.
Sorry, I think I asked about this last time, but I forget the conclusion. So, in the case where capital K is not, and just because you say xk is normal but not smooth, so like if capital K is not perfect and this king is not smooth, then what does this pick 0 xk over k look like? I guess, like.
So the pick 0 of xk over k will still be, well, defined as in the usual way. It will still be, well, yeah, I guess it will still be an abelian variety.
No. Geometrically, this thing it does not have to be reduced, right?
Right.
Oh.
But it doesn't. You can say it's geometrically
doesn't matter.
irreducible, right? It's normal and geometrically irreducible, but not geometrically reduced.
Right.
So you may have a an affine group, well, a group scheme that is not an abelian variety. Yeah.
But then I don't think that.
Oh,
Then
did I?
it can't have a narrow. If it's not smooth, it can't have a narrow.
Oh,
It can,
should I- should I
because
then-
you look at points in smooth. Yes, it can. I
But the
mean,
Neron model has to be.
there is no
smooth.
problem.
What's the definition? Are neural models smooth? Normally, smoothness is included in the definition of neural model. Because it's a property. If not,
okay.
then it's a
Yeah.
Yeah, but it is smooth.
But then,
It is a
It
group
is,
scheme that. So X is maybe not geometrically reduced, but that doesn't mean that the Picard group has a big problem.
Yeah,
But
no,
what is-
yes, there was.
No, it will just be
last
some
time,
unipotent extension, some extension of an abelian variety by copies of GA successor.
But GA
It's still smooth.
But GA does not have a neural model.
No, but it is also, but you're only going to test with schemes that are smooth over S. So you will never see that.
I don't understand. So
You won't see the non.
You will not see you will not see the nilpotents.
But then we.
Just the proof will work.
Right.
Yeah?
Hmm?
So it
Just
in
look
any
at the
case,
proof,
strict
it works.
The Picard scheme in any case is smooth. That was the criterion that the H2 of the fibers with coefficients in OX vanishes. So even if the curve is not smooth, then under our assumptions, the Picard scheme will still be smooth. So at least the statement that this Qx over S is a neural model, a priori it makes sense. There could still be that the proof doesn't work, but I think this is the statement as it is in the book. I do remember that last time I should have written geometrically integral somewhere where I wrote geometrically irreducible, but I don't remember if it was here. Okay, anyhow, so we started proving this last time by looking at an exact sequence of sheaves and taking push forwards. So we had this exact sequence of the multiplicative group on X. And this, so I forgot to say, to prove this, in general, we have to choose a rigidificator of X over S. So this was a suitable subscheme of X that is finite and flat over S, and such that a certain map is injective. and I will be the inclusion map of y into x. And then we can restrict functions on x to y. This gives a morphism of sheaves from gmx to I lower star of gmy. And we called gmx square brackets y the kernel. And this gives rise to a long exact sequence of sheaves on S. For the état topology, starting with f lower star of gmx, then to short of the multiplicative group on y, and then a thing which is called big x over s rigidified along y, and then the usual Picard sheaf. So this is the R1 at lower star of GMX. And in the same way, this thing is the R1 at lower star of this thing on the left. And the interesting property for us is, under the assumption that y over x is a rigidificator, this thing will be represented at least by an algebraic space. So this it is an algebraic space which is smooth over S. Okay, and what we're going to do is restrict to the sequence for line bundles of total degree 0. So I can just as well put square bracket 0 on these Picard things. So now we have at least presented our object of interest as a quotient of a representable thing. So from this, so we have now the last map from the exact sequence. Mapping to this big 0 has our q over x as a quotient. Maybe it's the quotient by the kernel that is dx over s. And to relate these two things to each other, we're going to let h be the kernel of the composed map. So from the rigidified Picard sheaf down to qx over s. So this subsheaf this thing, and then you can complete the diagram. So first, because this this map is 0, it vectors through here, and the quotient here of the rigidified Picard sheaf by h will have an induced map to qx over s. If we call this R and this R bar, then so this is automatically surjective because this is, and because h is by definition the kernel of this composed map. If you do a diagram chase or apply the snake lemma, then the conclusion is that R bar is an isomorphism. Okay. And now Well, there's slightly more details in the notes that will become available. But you showed now that H is flat over S. And then we get a quotient of this thing by a flat subspace, and then the general theorem says that this quotient is still representable by an algebraic space. And that is good because by our bar it is isomorphic to our Qx over S. So this implies that the quotient which is isomorphic to Qx over S is also an algebraic space. And then because we've quotiented out by Ex over S, it turns out that, so now in this quotient, the unit section becomes a closed immersion. And that will imply that Qx over S is also separated over S. And now we're in good shape because Qx over S is now smooth by the general effect mentioned earlier, and by construction it is also separated. And then there's another general theorem saying that in the category of algebraic spaces, smooth and separated group objects are schemes. So separated, say, algebraic group spaces schemes.
In general, or over the
Oh, I did not write down the conditions under which this holds. Well, at least over the yeah. Qx over S is a scheme and also automatically smooth and separated. Okay, so this proves the first part of the theorem.
I have to go.
Okay.
Can you give the camera to Steve Alberts? After the
Yes,
seminar, he will
yeah.
come to you.
Okay. Yeah, thank you. Okay, so now at least we've proved one crucial point, namely that Qx over S is a scheme, and it also satisfies some of the basic properties necessary for it to be a Neron model. So to prove that it is really a Neron model, we have to prove the two more things, namely that it is of finite type and that it satisfies the Neron mapping property. And finite type will come later. We will prove the Neron mapping property via the so-called weak Neron property. So this comes from a composition of two statements. There's a theorem due to Bay which, together with another statement, is going to imply that our thing which satisfies a certain weak Neron property is actually a Neron model. So this says if S, only for the statement of this theorem, is a normal Noetherian scheme, so this is just the base. In our case, this is just a DVR. Z is a smooth scheme over S. G is a smooth and separated group scheme over S. Then certain rational maps from Z into G can be extended to actual morphisms. So U will be an S rational map. So that is a morphism defined on an open subscheme. So U from Z to G. It's not necessarily morphism on all of Z. It's defined over an open subscheme on Z, which is dense in the fibers. And if U is defined in what is called in codimension at least 1, at most 1. So that means that the set on which it is not defined has codimension at least 2. Then U is in fact a morphism, so in other words it can be defined on all of Z.
Sorry, Peter, before you, in the diagram in the middle of the board, so there was this map R, and then there's a 0 after it, which is some kind of surjection, but what kind of, like, a surjection of what exactly?
Of sheaves on S étal. So this R is just the map from the exact sequence here.
Yeah. Oh yeah, sorry.
But then, can't you avoid going by the weak Neron mapping property? You could just prove the Neron mapping property directly. Because like,
Well, yeah, maybe. So I don't know. I just copied the proof from the book.
okay,
And it's possible that the proof becomes harder if you want to directly prove the whole Neron mapping property. But we'll see maybe during the proof. So now the fact that allows us to extend, to reduce the Neron mapping property to the weak Neron mapping property is that if X, now S is before, if X over S is smooth, finite type, separated as well, smooth separated and finite type, and suppose that the weak Neron mapping property holds, that is by definition the statement that every section of X K over the strict tensorialization, so the field of fractions of the strict tensorialization of R. If this is surjective, then we say that X satisfies the weak Neron mapping property. Then, if Z is a smooth S scheme, and U is a rational map on the generic fibers, then it extends to an S rational map over S. I will not prove this, I'll just note that, so I'll not prove either of these two statements. But from these, it follows that we can reduce the neural mapping property to the weak version. Now G is a smooth, separated group scheme of finite type. So just taking the things that satisfy the assumptions of both these results. Then the statement is that G is a neural model of a generic fiber if and only if it satisfies the weak neural property. Okay, so this is not hard to prove given the above results. Okay, using this we can give a sketch of the proof of the main theorem that was here at the beginning. The theorem on Qx over S being a neural model. So we already know that Qx over S is a smooth and separated group scheme. So we have to prove that it is of finite type by this corollary and that it satisfies the weak neural mapping property. I'll just very briefly say something about both of these. So for the finite type, we use the extra assumption in the theorem that X is regular. So finite type. We use the regularity to be able to use intersection theory. On the special fiber, so on the components of the special fiber. This gives us an exact sequence. So the central thing is the D, which is the divisors. Cartier divisors on X with support in the special fiber. Of such a divisor, we can take intersections with all the irreducible components. So I is the set of irreducible components. For any divisor, we can take its intersection with every irreducible component. That gives us a certain subgroup of Zi, which is in the kernel of another map. So this is a complex, not necessarily exact. Then it can be shown that for the finite type, that there's a canonical surjective homomorphism from one of the cohomology groups here. It's the kernel of beta modulo the image of alpha. To the component group of Qx over S. And in addition, if X is regular, then the left-hand side is finite. So this shows that, so now we have a group scheme which is locally of finite type with a finite component group, and that implies, again by a similar general result that was mentioned last time, that Qx over S is a finite type. So then the last thing that remains to be proved is the weak Neron property for Qx over S. So for that, we have to prove that the map from the points of the strict tensorialization of R to the points over the fraction field of that is surjective. So we use the definitions. We write these things as quotients. So the Qx over S is the quotient sheaf of the Picard sheaf, and then you show that they're also surjective on the sections. In fact, well, there, we don't even need that there. We just use that on the generic fiber. These things are just the same thing. We only do something on trivial with the special fiber. And we have to, so we still have to prove that this map is surjective. So for that we use the assumption that either small k is perfect or we have an étale quasi-section to relate these sheaves to the actual Picard groups. Okay, so let's see. First of all, this map is surjective. That is due to the assumption. So we have to prove that elements of this group can be represented by line bundles, and that uses the assumption then, so because this is surjective, it now suffices to prove that this map is surjective, because if we want to reach an element here, we choose an element here mapping to it, and if we can lift it to here, then we get our map of Qx over S R SH that maps to it. So, and finally, this is true, the surjectivity of this map is true by regularity of X, because